Let us look at a particle that is free to move in the vertical plane or the plane of the vertical circle. So gravity in this particular question is acting in the downward direction as shown. So G is acting in the downward direction. This is G. Let us say the particle is at the bottommost point of the vertical circle, and the particle is given an initial horizontal velocity u. We are going to assume currently that the particle is held or connected to the center with a string. Later, we'll also take in the assumption that instead of a string, we are using a rod. So this is the string that connects the particle with center C. The bottommost point is called as L because it is the lowest point. The horizontal point is called as R, and the topmost point is called as H. So we would like to analyze what happens with this particle as it traverses the vertical circle. So the initial horizontal velocity we are assuming the particle receives when it is at the bottommost point happens to be u. So let us say from the bottommost point after a certain time interval t, it traverses an angle theta. So this is the angle theta that it has covered. So if we drop a perpendicular from the point where the particle is, we can easily understand that if r is the radius of the circle, so the radius of the circle is r, then this particular length is equal to r cos theta. So the height that the particle has climbed is r minus r cos theta. So this is the height that the particle has climbed after a certain time t when it reaches the angle theta. So currently the particle is over here. So in that context, we can write down an equation by conserving energy. So we are assuming that the bottommost point is also the point of zero potential energy. So this point or this level rather is also the level of zero potential energy. Potential energy equal to zero level is this one. Potential energy is equal to zero. According to the potential gauge, we are free to assume any particular level as the potential energy equal to zero level, or any particular height as the potential energy equal to zero height. So now let us write down the equation between point L and point P where the particle has reached after a certain time t. Point P happens to be at an angle theta with respect to the vertical from the point L. So using energy conservation, initial energy of the particle would be only kinetic because at L potential energy is 0. So half mu square is the initial energy of the particle. So this comes out to be equal to half mv square, where v is the velocity of the particle at point P. This is v, the velocity of the particle. The magnitude of velocity happens to be v, plus mgh, and h we can write down as seen over here. H is r minus r cos theta. So clearly we can write down mg r 1 minus cos theta. So this is an energy conservation equation that is valid for any value of theta so long as the particle is traversing the vertical circle. So long as it does not leave the path of the vertical circle. Moreover, we can do a force analysis on the particle and understand that mg is the force that is acting in the downward direction. So mg will have a component. The component of mg that will be away from tension will be this component, and this component of mg is nothing but mg cos theta, because this is mg, this angle happens to be theta. So this component of mg is going to be equal to mg cos theta. So if we do write a dynamics or dynamical equation, then we get tension T that is acting towards the center minus mg cos theta, which in this diagram is acting away from the center. This is equal to mv square by r according to the dynamics of circular motion. So these are the two equations that are always valid. So now let us choose to analyze the first case, which is case 1 when it comes to vertical circular motion. So I'm going to do the analysis of case 1. Okay, so this is case 1. In case 1, we assume that the particle has not even reached point R. So basically we assume that 0 is less than equal to theta is less than equal to 90 degree. So not even the horizontal position has been reached. This essentially is case 1. So we need to here use only the energy equation, this equation that we have written down over here, and we need to use it at extreme points, that is at point L and at point R. So if we do use the energy equation, then we get half mu square, that is the energy at the bottommost point, is equal to mg r. Therefore we get u is equal to under root of 2gr in the limiting condition or the limiting case. Now it is very easy to understand that if we want the theta to be between 0 and 90 degree, then we have to keep the velocity u between 0 and under root 2gr. So long as the velocity is between 0 and under root 2gr, the theta traveled by the particle or the particle will not be able to go beyond point r. So this is where the particle will be lying. So once it goes over here, then it will come back over here, and then it will keep oscillating like this. It will keep going to and fro like this. Okay, so this is the case 1 wherein the particle is not even able to go up to 90 degrees. Now that we have analyzed case 1, let us analyze case 2 now. Okay, so in case 2, or rather let's analyze case 3. Let us skip case 2 because case 2's result will automatically get if we analyze case 3. So what is case 3? We want the particle to completely go ahead of point H, that is complete the vertical circle. That is case 3. So for case 3, we basically want theta greater than 180 degree. Mind you, we are deliberately skipping case 2 over here. We'll understand the reason very soon. So in case 3 itself, there are two different subcases. One wherein we have used a string and one wherein we have used a rod. So let us say we have used a string firstly. or we have used a rod. So at the highest point, the analysis is going to differ based upon whether we have used a string or whether we have used a rod. Let us see what happens. So if we have used a string, then the velocity cannot be 0 at the highest point. Okay. So what happens is the velocity cannot be 0 at the highest point. V at h not equal to 0. This is what happens. Because if the velocity were 0 at the highest point, then the particle would directly fall down under gravity. So if here the velocity becomes 0, then the particle would directly fall down under gravity. That is not allowed. The particle, we are assuming, has to necessarily complete the loop or complete the vertical circle. So at the highest point, we cannot put the velocity to be equal to 0. Whereas in case of a rod, there is compressive tension possible as well. So even if the particle has velocity equal to 0 at the highest point in case of a rod, then the particle is not going to fall down, it's still going to traverse the vertical circle. Even if the particle has 0 velocity at the highest point, it's still going to go ahead basically along the vertical circle. So for a rod, it is apparent that V equal to 0 at h. So this is the main difference. So for a string, V is not equal to 0 at h. So what is the value of V? So the value of V should be such that it should be minimum in order to minimize U, because U and V are related by this particular energy equation. So you can see that in order to minimize U, we have to keep the minimum possible value of V. Why do we have to minimize U? Because we are trying to find the limiting condition with minimum U such that the particle still is able to complete the vertical circular loop. So this is the condition that we are trying to find. What is the, see, if the velocity at the bottommost point is very high, then definitely the particle will be able to traverse the vertical loop. But we are trying to find the limiting velocity above which the particle should be able to definitely traverse the vertical loop. That's why in order to minimize U, we have to minimize V at the highest point. Now, in order to minimize V, we have to write down the force dynamical equation of V. So it is very clear that at the highest point, there are two forces acting. One is the force of gravity, mg, that is acting at the highest point. So this is mg. And another force that is acting at highest point is the force of tension, T. Both of them are acting towards the center. So in order to minimize the velocity v, so this is as per this equation also, cos theta happens to be equal to -1. So you get at the highest point T plus mg is equal to mv square upon r. In order to minimize v at the highest point, we have to put t equal to 0, because mg cannot be 0. mg is not equal to 0. That's the reason why at the highest point we need to put t equal to 0. Then in that case we get mg is equal to mv square by r. So mgr is equal to mv square. So apart from this particular equation, we obviously have the second equation, which says, which is basically the energy equation, which says at the bottommost point the energy is half mu square, then at the topmost point h, the energy is going to be equal to half m v square plus mg into 2r. This is the energy at the topmost point. Therefore, multiplying this entire equation by 2, I get mu square is equal to mv square plus 4 mgr. So from this equation we already know that mv square is equal to mgr. So I can directly write down mgr in case of mv square over here. So mu square is equal to mgr plus 4 mgr. So overall it is equal to 5 mgr. Therefore we get u is equal to root 5 gr. So essentially what are we understanding over here? In order for theta to be greater than 180 degree, we need to put u greater than equal to under root 5 gr if we want. So therefore the condition that we are getting over here is, therefore if we want theta to be greater than equal to 180 degree, we need to put u greater than equal to under root 5 gr. Now if we make the analysis in case of a rod, then we don't need the force dynamics equation, we only need the energy conservation equation because V is 0 at the highest point. So we can write down in case of a rod half mu square is equal to mg 2r, because at the highest point V is 0, therefore kinetic energy is going to be 0. So of course the rod that is there and the string that is there, both are assumed to be massless, so they do not have the energy component of their own. So we are talking about only the energy component of the particle over here. Therefore u is equal to under root of 4gr. So herein you get the analysis that in case of a rod which can withhold compressive as well as extensive tension, if theta you want to be greater than equal to 180 degree, then you will have to give a velocity u, horizontal velocity u at the bottommost point, to be greater than equal to under root of 4 gr. So once we do analyze case 3 in such a manner, then case 2 we can automatically get. How? Let us see that. So here case 2, in case of a string, what is case 2? Case 2 essentially is the fact that theta should be between the values of 90 degree and 180 degree. So 90 degree and 180 degree. Theta should be in between these two values. Therefore, clearly from case 1 and case 3 we can clearly understand that u should be between under root 2 gr and under root 5 gr, and here u should be between under root 2 gr and under root 4 gr. So this is for 90 degree less than theta less than 180 degree. So case 2 does not need to be analyzed if we do have the correct and perfect analysis of case 1 and case 3. Case 2 we automatically obtain. Okay, so this is the analysis of vertical circular motion, or a point particle that is moving in a vertical circle and has been given the velocity u at the bottommost point in the horizontal direction.